In this video, we're going to show that the derivative of the sine of x is equal to the cosine of x. Or to put it another way, if we defined y of x to be the sine of x, then y prime of x should be the cosine of x. And the proof takes 3 steps. Our first step is to prove this limit here. This little squigglies means that this formula on the left is approximately equal to 1 when h is small, and as h goes to 0, sine of h over h actually goes to 1. So let's actually look at that formula and what the numerical value of that formula is. So if we look at sine of h over h, right now it's not 1, but if I make h smaller and smaller, it approaches 1. So here's h right now. I have h set to 1. Watch what happens to this number over here, the 0.8415, as I make h smaller and smaller. It approaches 1, and I can get as close to 1 as I want by making h very small. Let me put this back up to 1 for a moment. Okay, so that we're going to have to prove. I mean, numerically we've shown it over here, but we haven't proven it, and we're going to prove that in a second. The other thing that we have to show is this here, that the cosine of h minus 1 over h is goes to 0. Well, it's approximately 0 when h is small, and in the limit it goes to 0. So let's actually look at that one. We're going to look at the cosine of h minus 1 divided by h. So right now it's notice it's a negative number. We would expect that because the cosine of h is always less than 1. So this difference here, cosine of h minus 1, is going to be a negative, and we're taking h to be positive. So right now it's not very close to 0. That's because h is still large. But as I make h smaller and smaller, it's going to approach 0. And I can get it as close to 0 as I want by taking h very small. Let's make it less than a million, 1/1,000,000th, for instance. Okay, there we are. It's now less than 1 over 4 million, roughly speaking. So I can make it however small I want. So we're going to have those two limits, and we're going to use them to prove this here. This is where we're heading eventually. You know, y prime of x is equal to the cosine of x. Let's look at those, the ingredients of those limits over here in this picture, just so you get comfortable with them. Remember what h is. H is an angle measurement, and we're thinking in radians. So if this is the unit circle, then we would picture h as this red arc starting down here at the x-axis and going up here. That's h. And then the sine of h is the blue line. The cosine of h is the green line. And 1 minus the cosine of h is this little region in here. You know, it's the unit circle. We're dealing with the unit circle, so the distance from the origin out to the circle is 1. So 1 minus the green line is 1 minus the cosine of h. So clearly everything's going to 0 as h goes to 0. But what our two formulas over here say is that the sine of h goes to 0 like h does. You know, the ratio approaches 1. So they become closer and closer together. At least the ratio becomes closer to 1 as h goes to 0. Whereas this is saying this other little segment, the little black segment here, that goes to 0 faster than h. So that's a geometric picture of what's going on. And let's now prove our two initial steps, and then we'll put them together in step 3. Now, step 1 requires that we look at 3 areas. So we're going to be looking at A1, A2, and A3, and they will have this relationship. A1 will be the smallest area, A2 is larger, and A3 is larger still. So what are those areas? Well, over here, A1 is the smallest triangle. A1 is the triangle with the green leg. That would be here to here. And the blue leg here to here. And the hypotenuse, the black line. So that's our smallest triangle. And that area is given by A1 equals, it's a triangle, so it's 1/2 the base times the height. So that's the cosine of h times the sine of h. All right, our next area that we're going to look at, A2, is slightly bigger. And it's the slice of the circle that is given by this line here, this arc. So it's think of it as slicing a piece of pie. And it's the area of that thing is given by this formula. A2 equals, if it were the whole pie, if you weren't taking a slice of the pie, of the circular figure, the area would be pi r squared, but r is 1 since we're dealing with a unit circle. So if we were talking about the whole pie, the area would be pi, which is kind of interesting. Now this is saying this is wrong because A2 is not the whole circle. So what fraction of the circle is A2? Well, its angle measurement in radians is h, and that should be compared to the whole circle, which is 2 pi radians. And then the fraction of the pi that we're dealing with is h over 2 pi. So we get the 1 there that says we're okay so far. And now finally we want to talk about A3. A3 is this triangle. The base is all of the unit circle, so to speak, out to the point where the circle actually intersects the x-axis. So that distance is 1. And this red distance up here is given by this formula, the sine of h times 1 over the cosine of h. The reason for that is the following. Look at the base here. The base is 1. Angle is h. So what's the... We can write the following formula. Let's do this. We can say that the cosine of h is equal to the base over the hypotenuse. Well, the base in this case is just 1. So the hypotenuse then, we can solve for the hypotenuse. And it's going to be 1 over the cosine of h. So that's where this comes from. The hypotenuse of the big triangle is 1 over the cosine of h. And now this is the opposite side of that triangle. So we know that the opposite side is given by the hypotenuse times the sine of h. So let's multiply both sides by the sine of h. And do a simplify. And this is the actual side, the hypotenuse times the sine of h, and that works out to be the sine of h over the cosine of h, which is what we have here. Okay, so let's put that in our picture then. Our area for that third and largest triangle is A3 equals 1/2 times the base, which is 1, and the side, which is the sine of h over the cosine of h. And notice we have 1s there, so that means I'm good so far. Now, let's see how we can take this inequality here and turn it into this expression down here at the bottom. Before I do that, let me point out one thing, make sure you're comfortable with this idea. So now here we're saying A1 is the smallest, and A2, and then A3. What do you think would happen if I inverted everything? If I turned everything over, took the inverse? Well, since A1 is the smallest, when we take its inverse, it's going to be the biggest. So these inequalities will actually reverse. Let me show you that here. We want to go to our ops and invert everything. And watch those signs. They reverse. And if I invert, it'll bring them back. So every time I invert, the signs have to change. So keep that in mind as we proceed here. Okay, so first of all, we're just going to substitute for A1, A2, and A3. And now I see a 1/2 in all those terms, in all three of those terms there. So the first thing I'm going to do is divide that out to simplify things. So let's go to our ops here. And I put my 1/2 in the auxiliary slot. Then I divide everything by 1/2. So we can do that since 1/2 is a positive number, so that will not disrupt the inequalities. Okay, now remember where we're heading. We're heading for the sine of h over h. So let's invert everything. We have an h here in the middle. I want to see the h on the bottom. So if we invert everything, we'll see the h on the bottom. And notice our inequality is reversed. We expected that. Let's do one other thing. Usually we like to put the biggest thing on the far right, because that's the way the number line is configured. We don't have to, but people tend to do that. So if I reverse everything, I'm keeping all the inequalities the same. I'm just reversing the order that I write them down. So same thing as before. I've just put the biggest thing on the right instead of having it on the left. All right, now what do I do next? Well, remember, I'm heading for the sine of h over h. I'm heading for this up here, sine of h over h. So if I multiply everything by the sine of h, and that should be one of my available choices. If I multiply everything by the sine of h, I get what I want. I get the sine of h is between the cosine of h and 1 minus the cosine of h. Well, now what does that mean then about the sine of h? Let's look at another picture here. All right, here we're graphing. The red line, or the red graph, is the cosine of x. The blue is the sine of x. And actually, let me put my h back to 1 so we can sort of see how this thing develops. The blue is 1 over the cosine of x, and the blue dot is 1 over the cosine of h. I've just evaluated the blue function at h, and the red dot is the cosine of h, and the green dot is the sine of h. So I'm just, this is the color scheme over here. And what we're showing down here analytically is that the green dot is between the blue dot, which is 1 over the cosine of h, and the red dot. And you can see that in the graph too. And what happens as h gets smaller and smaller? Well, the green and the blue are both going to squeeze down on 1, and so the green dot has to also squeeze down on 1. And so there's our proof that in the limit the sine of h over h is 1. So we've proven this. All right, let's go on to our next step, step 2. And we're going to start with this equality, this trigonometric identity, which is clearly true because remember we're dealing with that unit circle, and so by the Pythagorean theorem a cosine squared plus the sine squared equals the radius, which is 1. Alright, so let's manipulate that a little bit. We're going to take that and I'm going to put the cosine squared on the other side because I want to see 1 minus the cosine someplace. So let's do that. And that should be one of our choices here. Let's see. I don't see it. Well, anyway, let's put it in our slot by hand. So we're going to put the cosine of h in there, and then we're going to subtract it from both sides. Alright, and now we're going to factor this side over here. 1 minus the cosine of h squared factors into 1 minus the cosine of h. That's this piece here. Now this is, we could rewrite this as 1 minus the cosine of h, and this is the cosine of h plus 1. Okay, and now I'm going to divide both sides by h. So I put h in my extra slot there, and I divide both sides. Alright, and now I'm going to take this piece here on this side, and I'm going to divide both sides by that. So let's do that. Okay, now the reason I did that is if you look at this piece here, this is what I'm interested in. This is the formula that I'm interested in, cosine of h minus 1 over h. So now I've got it isolated on one side, and let's see what we can do with the other side. Well, we can take this h here, and I'm just going to, well, let me do it this way. I'm going to take this sine of h squared and split out one of those sines of h. So I take it away from there and I put it over here times the sine of h. And now let me group these together so that the program doesn't separate them. Alright, so we have this equality, and what is happening to this piece in here as h goes to 0? Well, remember that we proved back here that that's going to 1. So in the limit we can substitute that 1 there. So there's the 1 that, let me undo that and show you one more time. This thing here is just going to become 1 in the limit. Alright, and what about what's left? Well, as h goes to 0, look over here at this picture. Look at the blue line. Sine of h is going to 0. And what about the cosine of h plus 1? What's that going to? Well, the cosine of h is going to 1, so this denominator is actually going to 2. So we can make that substitution. We can pass to the limit. That's all we're doing right now. We're passing to the limit. And in the limit, that is equal to 2. And now notice this little test says, you're not right, you're not quite there yet. Well, that's because we haven't gone quite far enough. If I make it my h even smaller, I can get those as close as I want. So in the limit, they're equal. So let's make that substitution. Alright, and then finally in the limit, the sine of h is equal to 0. So I can substitute a 0 for that. And look, again, it's saying, well, yeah, that's pretty close, but it's not exactly right. And, it's never going to be exactly right, but I can get it as close as I want by making h ever smaller and smaller. And there it's, real close. So let's make that substitution. And now let's just simplify the whole thing. We got a 0 on this side, so what's going to happen when I simplify? It should go to 0. And if I reverse it, I get this formula here. Almost, what I have to do now is negate both sides. So I can negate 0, it's still 0. And if I negate the left-hand side, it's going to be just what I want. Okay, so that's the formula that I wanted. So we've shown this now. All right, now final step. Final step. Step 3. This is our definition of the derivative. Y prime of x is approximately equal to this formula, and as h goes to 0, it becomes an equality. So in the limit, y prime of x is equal to this formula here. So let's see what that formula works out to be in the limit. And to do that, we're going to use our result that we proved in the last module, which is the sine of a sum can be rewritten as sines and cosine. This is our silly cops plan, silly capers. So it's sine cosine plus sine cosine. That's what this thing is going to become. So let's make that substitution. That's one of our conditional ops. That's this one here. All right. And now, notice it's the whole thing over h. I'm going to actually distribute that h. So let's just do expand all terms, and that distributes the h. And the reason I did that is I now see here the sine of h over h. And we know that in the limit, that goes to 1. That's exactly what we proved back here in step 1. So let's take the limit by making that substitution. When we do that, you'll notice that what we're left with is cosine of x times 1. So this is how the cosine comes into the picture at last. So I make that substitution. Now I have cosine of x. Now what about what's left? Well, let me do this. I have a cosine of x over here. I want to temporarily put it on the other side just for convenience. So if I tee it up and I add it to both sides, nope, that's not what I want. I want to subtract it from both sides. Okay, now look at this side over here. It has a sine x and a sine x in the two terms, so I can do a factor all terms. And I get this. But remember what our second step was. That is the cosine of h minus 1 over h goes to 0 as we take the limit. But I have, it's split up, but I have the cosine of h minus 1 divided by h. So those two terms are going to come together and go to 0 as h goes to 0. So that means the whole right-hand side goes to 0. So let's make that, or take that limit essentially is what we're doing. If we substitute this in there, we're implicitly taking the limit. So we get this expression. And now let's add that cosine back just to get it in the form that we finally wanted. And now, since we've taken the limit, we could change that approximately equal to equals, and we have our formula. So this is what we ended up with. All right, so quick review, the big idea. The big idea is we have two limits that we want to prove, and we prove them by looking at the areas of these three triangles, and we get a relationship between the areas and do some manipulations and prove those two limits. And then we use our formula for the sine of x plus y. That is right here, sine of x plus y, and do some manipulations and we get what we want. So now we have another derivative, and we can do the same sort of thing and compute the derivative of the cosine. But it's actually easier to wait, and we're going to develop some general rules for derivatives, and then we can compute the derivative of the cosine very simply without going through all these steps. It'll just be essentially one step. So we'll do that maybe not the next module. Next module we'll look at some general rules for derivatives, and then the subsequent module will use those rules and this result to derive the derivative of the cosine, and the derivative of the tan, and the secant, and the cosecant, and the arctan, and the cosecant. So once we get those general rules in place, a whole lot of derivatives are derived from this initial proof that the derivative of the sine is the cosine.